Good afternoon, ma'am.
Good afternoon.
Good afternoon, ma'am.
Ma'am, please try if you are able to present your screen.
Are you going to give some introduction or should I just start?
Yes, ma'am.
All right, I'll just start. No issues. If there...
No, ma'am.
Ma'am, please.
Ma'am, they will be giving the introduction. They just want to keep a check whether screen can.
All right.
Okay.
Yeah.
Okay. Should I begin?
Is the screen
Yeah,
visible?
Palak, you can...
Is the screen visible?
Yes.
Yes, ma'am.
Yes,
It's
ma'am.
perfectly visible. Okay. A very good afternoon to all present here. I welcome you all to the second session of the last day of our 1-week ATAL FDP on Foundation of Data Science and its Applications, Advanced. We have Dr. Mrs. Amita Dev, Honorable Vice Chancellor, IGTTUW with us. I welcome you, ma'am. Dr. Amita Dev, Vice Chancellor of Indira Gandhi Delhi Technical University for Women, is a true leader, excellent administrator, and a passionate researcher. She's doing extensive research in the field of deep neural networks, speech processing, speech modeling, speech recognition, speech synthesis, etc. Having vast experience of more than 3 decades, she has unparalleled track record of administration, quality teaching, innovation, and research. She has published more than 123 research papers in renowned international and national journals and conference proceedings. She is an avid speaker and a great motivator. She has been invited at various national and international forums. In recognition to her valuable and worthy research contributions, she has been conferred with many awards like National Level AICT Young Teacher Career Award, State Level Best Teacher Award, National Level Best Engineering Teacher Award, International Econs Education Excellence Award, and numerous appreciation letters from state and center for exemplary performance and outstanding contribution in the field of technical education. Dr. Amita Dev has introduced a series of innovative practices and reforms as the Honorable Vice Chancellor of our university. Under her esteemed guidance and able leadership, IGTTU has achieved several milestones in a short span. With this, I sincerely request Honorable Vice Chancellor Ma'am to begin with the presentation. Ma'am, we really look forward to learning a lot from this session. Thank you so much.
Thank you very much. I hope I am loud and clear.
Yes, ma'am.
Yeah. So, dear friends, today I thought let's talk a bit more technical about data sciences. I remember during my first talk, I was looking forward for an opportunity so that we can discuss something more, what models are being deployed for data sciences. And I'm glad I have been given this opportunity to interact with esteemed faculty members once again. And the topic of our discussion today would be deep learning models for data sciences. And out of the deep learning models, I am looking at convolution neural networks. So data sciences, as you all know, a multidisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured and unstructured data. Since I'm talking of a data which is structured and unstructured data, and also we also say that the data sciences is a set of tools to make sense out the business problems using disparate data sets. Now, these disparate data sets, it could be your temporal data, it could be spatial data, it could be images data, it could be any kind of data, noisy data, noiseless data, and so on and so forth. So today we are looking at that in case if we have to use data sciences and extract data out of images, what are the latest tools and techniques which are available for extracting data from the images? And nowadays, This has become, it has a vast application, whether you do face recognition, object detection, object recognition, and so on and so forth. In data sciences, this is really very, very useful. And as you know, if I look at a data science also, it has an amalgamation. It uses the tools and technologies which are deployed in artificial intelligence, which is a superset. Machine learning is a subset, and somewhere in the machine learning, now the latest trends are deep learning. So I'm going to talk about convolution neural networks as a part of the deep learning. Very often, it's a very basic slide. Very often the confusion always comes to the mind that why should I go for a deep learning? How does the system is different between machine learning and deep learning? As you know, in the case of machine learning, which is definitely a subset of AI, and it includes abstruse statistical techniques that enables machine to improve the task with experience. If you look at onto your left hand side, the input which is going as an image of a dog, we are doing some feature extraction, classification, and output. Now, in the case of machine learning, this feature extraction, these are handcrafted features. Or I may say that there is no learning as far as feature extraction is concerned. So that's why I'm saying feature engineering, which we are deploying, it is as if these are handcrafted feature extraction. There is no learning happening in the feature extraction. The learning and the weight updation in the case of your traditional machine learning is happening only at a classification. Now, if you look at onto your right hand side, the image where input is again going as a dog, and deep learning is not working on handcrafted feature extractions. Instead, there is a whole amount of learning which is happening at feature extraction plus at classification, and we are getting an output. So deep learning, which is also further a subset of a machine learning, it is comprising of algorithms that is permitting the software to train itself to perform various tasks, right from speech recognition, image recognition, object detection, object verification, speech synthesis, and so on and so forth. The domain of this deep learning is huge, and it is deploying multi-layered neural networks with the vast units of data. When I say vast units of data, deep learning algorithms, they are hungry about data. If they have to work fine, it has to use vast units of data. When we use a single perceptron and a multi-layered network perceptron, these are also very basic things which I'm talking, and then we'll go on to convolution neural networks. If you look at a single perceptron, it will essentially have only two layers. It is comprising of input layer and output layer, and it learns with linear functions. But you understand, in today's environment, if we talk of real-time applications and what is happening, there's nothing called as linear functions. Every behavior, every characteristics in a real-time environment is non-linear. And usually single layer perceptrons, they will perform binary classification, does not allow back propagation. The moment the back propagation is not there, it means weight updation is not happening. It means I cannot optimize my loss function. So learning is not happening. If weights are not getting updated, there is no concept of the learning. And it is dealing only with the linear separable functions. The way you see a line which is denoted by mx plus c, if you have drawn a line, so it is linearly separable, which is anything which is above the line is one set, anything which is below the line is another set. But again, if I'm looking at the images, for example, on a Facebook, if you see many friends' photographs are there and my image is being abstracted by my friend's image also, still we are looking at the models that it is able to clearly distinguish my image from the other person's image. So it means the patterns which we are looking, they are not linearly separable. In a real-time environment, what you get is non-linear functions you work upon, because you are dealing with real-life examples which are non-linearly separable functions. That's the reason multi-layer network, they have become very, very popular, and we deal with perceptrons. It means 3 layers input, minimum 3 layers, one or more hidden layers, and an output layer. So till the time we were working with the machine learning algorithms, we were dealing with maximum 1 hidden layer, 2 hidden layer, 3 hidden layers, or 4 hidden layers. The question comes in, why not more layers? We have always been dealing with maximum 3 or 4 layers, and this concept was carrying on till the last decade. It was only this 2010 onwards we have seen that deep neural networks have penetrated in the real environment at each and every domain. Because number one, high computing power, definitely you need more and more hidden layers, more computing powers. Another was that till that we were working only with different kind of the activation functions. But then when ReLU came into picture, the ReLU has transformed how we are dealing with the multi-layer networks, and the hidden layers, they could do exceedingly well with ReLU. That was the one advantage we got with ReLU activation function. Then it is able to learn. If you deal with multi-layer, it is definitely able to learn non-linear functions and able to also known as universal functions. And definitely when I'm learning means it has to allow back propagation, because in the advent of back propagation, the weights which were assigned, those weights are getting updated, and it is able to deal with non-linearly separable functions. And definitely there is something called as supervised models or unsupervised models. So if I look at classical neural networks, multi-layer perceptron is one example of your supervised model. Convolution neural network is another example of your supervised model. Recurrent neural networks, which deals with the sequential data, which is your temporal data and the sequential data. When I deal with the speech signals, when the speech is being spoken, it is an example of the time. So it is a sequence, because the word which has been uttered previously has been uttered at t minus 1 second, and then it is coming at t second, and then t plus 1 second. So there what we deploy is a recurrent neural network, which is dealing with the sequential data. And in the case of unsupervised models, as you are all aware, you deal with self-organized maps, Boltzmann machines, autoencoders, decoders, transformers, and so on and so forth. So let's now concentrate and go on to convolution neural networks. So what is convolution neural network? So this convolution neural network is a big picture which I have shown at the top. I will be discussing about this, but let me just say what is a convolution neural network. A convolution neural network is a class of deep neural networks, and it is usually deployed to analyze visual imaginaries. It is doing exceedingly well in the visually imaginary fields. They're also known as shift invariant. And these are shift invariant or space invariant artificial neural networks. When I say shift invariant, it means you will come to know about this, that the shifting is not having any issues when the filters are being used, and the filters are moved with a stride of 1 or with a stride of 2. This model is shift invariant, and it is also space invariant, and it is based upon shear weight architecture and translation invariance characteristic. These two words are very important, shared weights. In the case of convolution neural networks, we see two things, how it makes it different from the multi-layer perceptrons and others, or your regular feed-forward neural networks. Number one, it has shared weight architecture. Number two, it has sparse connections. Number three, it is translation invariant. So these are the characteristics of convolution neural networks. Now, what is the motivation? Whenever we come up with the new models, new technologies, I'm sure there has been certain restrictions, certain abstractions were there in the existing models, which motivate us to move and look forward for some better models. Now, if you look at on my left hand side, one is your multi-layer perceptron model. In the case of multi-layer perceptron, as the name indicates, it can have multiple hidden layers. For simplicity's sake, I have shown you one hidden layer. And if you see input layer, how many neurons I am showing at the input layer? These are 6. Now, all these 6 neurons at the hidden layer 1 I have 3 neurons. So every neuron from the input layer is fully connected to every neuron in the hidden layer. So it means the connections which you see, these are 6 input neurons, and every input neuron is connected to every neuron in the hidden layer. Imagine if I have 1024 as my input neurons and I have 800 in my hidden layer as a neurons, the number of interconnections which you will witness would be 1024 multiplied by 800, which is at hidden layer 1. These many connections are there. What do you mean by these many connections? When I'm talking about these many connections, it means these many weights would be there. So I'm talking about 1024 multiplied by 800 is the kind of the weights which would be there. Or for simplicity, let me take it 1000 multiplied by 800. That will make it 8 into 10 raised to the power 5. That is the kind of the connections which you see from input layer to hidden layer. And then from hidden layer 1, if you're going to hidden layer 2, so every neuron at a hidden layer 1 is fully connected to every neuron at a hidden layer 2. Again, let me take an example. Now at hidden layer 1, I took an example of, let's say, 800. Now at a hidden layer 2, suppose if I have 100 neurons at hidden layer 2, the number of interconnections which would be witnessed would be 800 multiplied by 100. So that would be 8 into 10 raised to power 4 interconnections, and those many weights, and so on and so forth. So look at the complexity which is involved at every stage, and those many weights, and hyperparameter tuning has to happen for those many weights. Activation functions are involved for those many weights, and during back propagation, all these weights will be updated, and we will be computing our loss function based upon the weight updations. It's a very, very complicated, very time consuming, so many connections and interconnections. Now, if you look at convolution neural network on your right hand side, you will be very astonished to see my input layer. Again, I'm showing 6 neurons at an input layer. If I look at a hidden layer, perhaps every neuron in the input layer is not connected to every neuron in the hidden layer. If you see at input layer, neuron 1 and neuron 2, they are just connected to neuron 2 in the hidden layer. Similarly, neuron 3 and neuron 4 in the input layer is connected to neuron 3 in the hidden layer. Again, neuron 5 and neuron 6 in the input layer is connected only to neuron 4 in the hidden layer. So this is what I call it as sparse connectivity. They are not fully connected, but I'm having a sparse connectivity. Immediately a question comes to the mind, in case if I'm doing a sparse connectivity, is it that am I losing information? Is it that I am sacrificing on the information? Not really, because my subsequent slides will show you, though apparently at an input layer, neuron 1 and neuron 2, though it is connected to hidden layer 2 neuron, eventually when the connections become deeper and deeper, when I will deal with more and more hidden layers, then the patterns would be learned immediately. More and more deeper layers will allow me to capture all the patterns. So I will not be losing any information. Instead, it will give me more computationally, less expensive, less number of interconnections. Now here, if I talk of, if there are 1024 neurons, or for simplicity, if I say it is only 1000, and at the hidden layer, these are 800 neurons, but every 1000 is not really connected to all 800. Perhaps they are connected to, let's say, to 80. So in that situation, my number of connections has reduced to, it will be 8 into 10 raised to power 4, and rather than 10 raised to power 5, which was happening in NLP. So you can see the number of interconnections have drastically reduced. So convolution neural networks are giving me sparse connectivity, but not compromising on to the pattern and recognition. Why we use convolution neural networks for images, for face detection, object detection, and so on and so forth. If you look at images, basically, if I look at a arena which is close to me, so that is the arena which matters to me. If I'm looking at the pixels which are near me, they matter to me, and the pixels which are not very close to me, perhaps I am not losing much of information. So when we deploy filters on these convolution neural networks, they're able to learn, and they're able to learn very, very effectively and efficiently. So convolution neural networks are simple neural networks that uses convolution in place of general matrix multiplication in at least one of these layers. So this is once again the example. If you look at a 3-layer neural network, you have a hidden layer 1, hidden layer 2, and an output layer, and you are dealing with the dense connections. We call it as a dense network. In contrast, when you're looking at a convolution network, it arranges the neurons in 3 dimensions. That is your width, height, and depth, as visualized in one of the layers. If you see input layer, I'm treating it as a 3-dimensional layer. Then somewhere in the middle, it is coming up as again a 3-dimensional layer, which I will call it as filters, I will call it as kernels, and then multiple filters, multiple kernels. And they are dealing with the sharing waves with sparse connectivity. And then you see again, I will do some kind of a pooling operations and some kind of padding and pooling operations. And what you get is again a 3-dimensional neurons, which are with the width, height, and depth. And finally, you end up with the classification. You wanted to classify, if you had 1,000 images, you want to classify that image, whether it is a dog, cat, or in the case of forensic science, whether it is this particular theft or a crime which has been happened by one of the criminal, and you have, let's say, 1 million images, perhaps you want to figure out which image is this. So it will be able to do it. Now, when I talked about from the input layer, I will be deploying some kind of a filter. Now, what that filter would be. So consider that you have a 5x5 image whose pixels are having a value 0 and 1, because you can see on the left hand side, I have taken an image which is 5x5. It has values like 0 and 1. And what I'm going to deploy on that particular image is a filter. I can call it as a kernel also, a filter, which is of a size 3x3. What is the purpose of a filter? Now, filters, if you look at these filters are mimicking the way my brain also works. In our brain also, if you see that you have a visual cortex, and visual cortex also has layers, layer 1, layer 2, layer 3, layer 4, layer 5, layer 6. Now, the purpose of this visual cortex, when I see any image, the purpose of this visual cortex and these layers would be, in a very hypothetical example I'll give for better understanding, that the layer 1, let's say it is meant to detect the edges. Layer 2, maybe it is meant to detect the vertical edges. Layer 3, it is meant to detect the horizontal edges. Layer 4 is again trying to read those images and the characteristics of those images, and making the other non-important pixels blur, doing blurring on those non-important pixels, and so on and so forth. So the same concept has been taken up in the case of convolution neural networks. So considering that if I have an image which is 5x5, I want to deploy a filter. Filter is like that layer which I have in my brain with the visual cortex, layer 1. This filter could be, it could be your vertical edge filter, it could be your horizontal edge filter, and so on and so forth. And let's say this filter is of a matrix 3x3. And then it is superimposed upon this image matrix, and as you can see, it is moving. So this matrix filter is placed with a stride. Currently, I'm placing it with the stride of 1. So once you place with the stride of 1, what do you mean by stride of 1? It means after completing the first top matrix of 3x3, it moves with the stride of 1. It shifts itself with the stride of 1, as you can categorically see. And what it does, it multiplies the image values, the pixel values, with the values which are available in the matrix and places it in the convolved features. This is a feature mapping. In your conventional machine learning algorithms, you are not learning the features. Here in the case of convolution neural networks, we are trying to have convolved features. We are doing a feature mapping. Convolution of an image with different filters. I said filters can be called as a kernel, can be performed, let's say, for a 2D image. It could be for identity. I can have a convolved image and I can have a filter. I can have an edge detection filter, which is trying to detect only the edges. And let's say if I have a person sitting in a park and there is a sky being shown, I'm interested only in that person because I'm going to detect whether that person is a criminal or no from the kind of the images which have been given. So I am just not interested in that sky and the green carpet grass which is being shown. I'm interested only in the edges of that particular person. So I will be deploying will be the edge detection kernel or a filter. Or if we are interested in sharpening the image, so the filter could be for sharpening the image. If you want to blur the rest of the boundaries, that sky, the tree, the carpet grass, green grass, then I can deploy various blurring kernels. One of them could be a Gaussian blurring kernel and so on and so forth. For example, let's say this is now, I have given you the example of, let's say if it's a Taj Mahal, and I'm interested, if I've been given a task of classification, given this particular image, find it out, is it a car, is it a monument, is it a dog, or is it a cat? So what I am interested in is this monument, and I am not interested in the blue sky, the corresponding trees, and the pedestrian path which is being shown, and the carpet grass which is there on the extreme right and on the left hand side. So what we are going to do is to blur the areas of the green, of the blue sky and the rest of the things. We are going to do the sharpening of the Taj Mahal, and we are going to do the edge detection for this Taj Mahal. So these are the kind of the kernels which we can deploy. As I told you, if I have been given an image, it's a raw pixels, and what I have to do is a classification. Let's say if we want to figure out it's a car, bus, monument, or a flower. So in your machine learning techniques and typical machine learning techniques, you will be doing an edge detector and then send it to the classifier. And it will tell you whether it's a car, whether it's a bus, monument, or a flower. When we go on to our feed-forward neural networks or a multi-layer perceptrons, if you're deploying, as you know, the very famous the feature extraction techniques for images in 2010, 2012, these were very popular. We deploy Swift or a Hog feature extraction techniques. But then when you deploy Swift or a Hog feature detection techniques, eventually there is no learning happening. These are, I'll call it as handcrafted features. There is no learning happening. There is only handcrafted features, no weight updation, and no learning. And then you used to have deploy learning in the classifier and then come up with a classification, and you are just learning the weights of the classifier, saying whether it is a car, bus, monument, or a flower. But in the case of your convolution, the things, they vary. You have an input, you will deploy certain feature extraction techniques in terms of having the kernels and the filters which will be learning, and you, instead of your handcrafted kernels, we, such as edge detectors, we are learning multiple and meaningful kernels. When I'm talking about multiple layers, as I told you, in our visual cortex in the brain, you have layer 1, layer 2, layer 3. Here also, what we are going to deploy is kernel, but not one kernel, multiple kernels. And then they are going to learn the weights of the classifier. Because one of the kernel may be interested to find out the edge, other kernel is finding out to sharpen the image, third kernel is doing a horizontal edge detection, fourth kernel could be for the vertical edge detection, fifth kernel could it be that it is trying to flip the image and so on and so forth. So we can learn multiple layers of meaningful kernels in addition to learning the weights of the classifier. Simply by treating these kernels as parameters and learning them in addition to the weight of the classifiers using back propagation will lead me to the convolution neural network. Another thought comes in our mind when we deal with the feed-forward neural networks and with the dense connections. You know, during backpropagation, every weight gets adjusted and there is a learning happening at every weight. Now the question comes, when I'm deploying filters, is the weight getting updated in the filters also? The answer is yes. The weights are getting updated in the filters also. And when I'm dealing with example of, let's say, 2D or a 3D image, it is sliding the kernel over the input image. I have already shown you the sliding is happening with the help of kernel. It will all depend upon the size of the kernel and the amount of the stride which we are taking. Let's say if you have an image of 6 cross 6, I'm asking a question. If you have an image of 6 cross 6 and you're deploying a kernel of 3 cross 3, what is the output image you are getting? Input image 6 cross 6, let me call it as N. Kernel, let me call it as a F, it is a filter 3 cross 3. What is the output matrix? I had shown you in my first slide, the output matrix which I was getting was 4 cross 4. It means the input was 6 cross 6, kernel was 3 cross 3, output matrix which I got was 4 cross 4. So the formula remains as, if N is the size of my input matrix, F is the size of the filter, the output which I'm getting is 4. It means it is N minus F plus 1. N is 6, F is 3 plus 1. So 6 minus 3, 3 plus 1 makes it 4. So the output of the matrix which I got was 4. Again, the question comes, input was 6 cross 6, output is 4 cross 4. Have I lost some information? Or if I want the output to be the same, it means output also has to be 6 cross 6. So what I have to do? I will deploy some technique called as padding. I'll come down to that in case if we are interested. The second question is, am I losing some information? Apparently, it looks you're losing information, but when you work with deep hidden layers, you are eventually not losing any information. And the resulting output, what you are getting is a feature mapping. And now you have seen how is it different. Otherwise, we used to use a SIFT and the hog for finding out the feature extraction. And here, the feature extraction or a feature mapping, it is not handcrafted. Instead, we are doing a feature mapping. And we can use multiple features to get multiple feature maps. So that's an example. If you see, consider if I have a RGB image. So I've given you R, which is shown as red, the green, which is shown by G as green and blue. So this is my 3D image. So if it is working with the 3D image, I will call it as a volume because it has a height, it has a width, it has a depth. Now we slide the volume over a 3D input and compute the convolution operation. Here, what will happen is the filter will move on a 3D image and assume that filter always extend the depth of the image. In fact, we will do a 2D convolution operation on a 3D input because this convolution operation is happening in a 2D form. So though you are working on a 3D, but you will have a convolution operation on a 3D input because the filter will move along the height and the width and not along the depth. As a result, the output will be 2D. That was in fact the question which I wanted to pose, that if you're working on a CNN for a 3D image and you are deploying a filter which is moving on this 3D image, what will be your output? The output from that filter will be your 2D image because this filter is moving along the height and the width, but not along the depth. Obtaining a 2D image, we can apply again. You will apply again multiple filters and multiple feature maps will be obtained. It is just an example. I was talking to you. I'm glad that I have this slide with me. there is a visual cortex of the brain for visual data processing. If you look at the brain, and there is a visual cortex here, and this visual cortex at the back of our brain, it has various layers, and then these layers are responsible for edges and corners, form feature groups, detect high-level objects, spaces, and so on and so forth. So the convolution neural network is getting motivated by these layers in our visual cortex. In your feed-forward network, definitely you can see if I want to learn, let's say I have an image of a letter called as 2, and this 2 is having 4 cross 4 pixels. So how many pixels? These are 16 pixels. I'm just pulling it and stretching it on a straight line. So my input neurons, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are 16 neurons. So 4 cross 4 pixels, if I stretch them into a line, it will become 16, and 16 are being shown. Now these 16, I have shown you one hidden layer. On this hidden layer, first neuron, you can see the kind of the dense connections which you have. And subsequently to every neuron, you are having dense connections. And then you are going to the second layer, you are going to the third layer, you are going to the fourth layer. And finally, at the top is my output layer where I'm trying to figure out that how many, which is the class of the digit which I have recognized. This is my normal feed-forward neural network. Now, if I go back to 2, in the case of my convolution neural network, so you can see in the case of convolution and neural network, I have 2. 2 is being shown again 4 cross 4. When I'm dealing with 4 cross 4, when I'm stretching these neurons, they are being shown like this. And when I'm dealing with the first neuron at a hidden layer, which I'm calling it as a hidden layer H11. Now this H11, to where it is connected. H11, it is connected to, please see, 1, 2, and 3 and 4, it is not connected. Then it is connected to 5 and 6 because my filter is 2 cross 2. So when I will impose that filter of 2 cross 2 on this particular image, so I am getting connected to neurons which are 1, 2, 5, and 6. And that becomes my H11. Similarly, when I look at H12, if I move with the stride of 2, I will be working on 3, 4, 7, and 8. I hope this is clear because it is 3, 4, 5, 6. I'm not dealing, then 7 and 8. So this is what which is precisely being shown. H11 is getting inputs from neuron 1, 2, and then from 5, 6. H12 is getting from 3, 4, and then from 7, 8, and so on and so forth. This is what I'm calling it as sparse connectivity. So this sparse connectivity, it is reducing the number of parameters. Now, my next question was, by having a sparse connectivity, am I losing any information? I say not really. Despite the fact that you have a sparse connectivity, you have less interconnections, you are not losing. Look at this particular image on your left. At the bottom, I have neurons, which is 1, 2, 3, 4, 5. At the hidden layer, the one I have made it red, the second neuron on the hidden layer, it is connected to the first and to the third. So apparently it will look that at the learning of this neuron H12, it is happening only from H11 and H13, from the neuron N1 and N3. It means it is losing the information from N2 and from N4 and N5. But you see very carefully, if you look at the hidden layer and look at the hidden layer neuron number 4, it is learning from the neuron N3 and N5. But if you look at the hidden layer 2, the neuron at hidden layer 2, which is your H23, it is learning from your neuron, which is at H12 and H14. So you see the learning has happened at the hidden layer 2. It is just a small example. And nowadays, when we deal with convolution neural networks, you are dealing with not 2, 3, 4 hidden layers. You are dealing with 100, 200, 256 hidden layers, thanks to activation function ReLU. So you're not losing any information. So this is what I showed. If this is a kernel 1, you can see In the orange, there is a kernel 1, which is there. You can see a kernel 2, which I have shown. So, but there is a weight sharing happening. So we are learning kernels that they are detecting the edges. Since they are detecting the edges, should we not be applying the same kernel at all parts of the images? Hence, we are deploying kernels at all parts of the images because they're detecting the edges, and hence CNN uses weight sharing. So you look at this particular image, as I told you, the image, if I am dealing with the RGB image, so you have a red input channel 2, which is green, input channel 3, which is blue. Now I have deployed, let's say, 3 kernels. As I told you, if you are deploying a kernel on a 3D image, what you are getting is a 2D output because kernel is working on the height and on the width and not on the depth. So I have deployed kernel 1 on the red, kernel 2 on the green, and kernel 3 on the blue, and that learning is happening. Also, you can see some zeros at the top, input channel 1. There is something in the light blue, but I'm showing you something in the white also, which is all flooded with 0, 0, 0. What is the purpose? The purpose was, since the matrix which you were getting earlier, as I told you, 6 cross 6 was my input, filter was 3 cross 3, my output matrix was becoming 4 cross 4. In case, if you are interested to have the same output as your input, what I deploy is a concept called as padding. In the padding, what happens is, think this light blue is your house. So what I'm doing is, outside my house, I'm giving a circumference. We have constructed a boundary. And that boundary, what it is housing is all 0, 0, zeros. By deploying this boundary, I call it as padding, and these are zeros. By deploying this boundary, I'm able to get the output. If you see on your right hand side, the output, it is of the same type. What was your input, which was 1, 2, 3, 4, 5, which is 5 cross 5. So you have got 5 cross 5 as an input. Now, the question will come to your mind, what is padding? Padding is only, it's a kind of a cushioning. As I give you an example, you have a house, consider light blue color is your house, and you're constructing outside a circumference which is protecting your house. Here, in case if you're interested to protect the same size of the image, what was your input? What you are going to deploy is a padding. And with this padding, I have given zeros. There are various technologies which you use. Rather than 0, the padding can also learn the leftmost pixel which contact it is. If I say the pixel is having a value in your present context, it is 156. So what you can do is replace 0 with 156. Next is 153. You can replace 0 with 153. 149, you can replace it with 149. And also, if you see, this padding is also giving me an edge detection also. It is also helping. But usually what we do is, we don't replace the padded value with the immediate value of the neighbor. Instead, 0 is something which is commonly deployed. So that is the purpose of the padding. Now, this is the way your convolution neural network, it looks like. You have an input. Input I have shown you as 28 cross 28 cross 1. Why? Because it is 2D image and not a 3D image. Let's say I have started with a kernel which is 5 cross 5 kernel. It's a 5 cross 5 kernel, but there is a whole layer of kernels. As I told you, we are not, and this is having N1 channels. N1 channels are basically the number of kernels which are there. That is the number of kernels which you have put in. And these are N1 channels, that's the number of kernels. And then what I'm going to do is the max pooling to it. You are seeing that I have deployed a word called as max pooling. So with this kernel, the feature mapping which I have done on the next layer, what I'm doing is a max pooling. I will come down to what is max pooling. Once I have made my matrix, let's say the matrix is comprising of 2 cross 2. Consider hypothetically 2 cross 2. The values are 1, 2, 3, and 4. When I deploy a max pooling, what it will do? Out of this 2 cross 2, values are 1, 2, 3, and 4. What is the maximum value? Maximum value is 4. So it is going to shrink my 2 cross 2 matrix to just 1 × 1, and the value will remain as 4. I think I will have slides which I will show you. That's the reason, apparently, when you look at this particular diagram, the max pooling has reduced the size, and you can see a shrinkage happening after the N1 channel. Again, you are at N1 channel with the max pooling, but you see a shrinkage happening. Then when I apply a max pooling of 2 × 2, you can expect a shrinkage which is of the tune of 1/4. Then again a convolution 2, again I have a convolution layer which is of 8 × 8, and it is having N2 channels. And with this N2 channels, I have provided a valid padding also. Now you have understood a padding. Again, I'm going for a max pooling, which has made it, it has shrinked it, and which is by 2 × 2. Hence, the shrinkage will be of the tune of roughly of the tune of 1/4. And after that N2 channel, there'll be multiple. And at the end, a convolution neural network will see a flattened layer. What do you mean by flattened layer? It means you have again come back to dense connections. Now, whatever are the neurons which are left, you will see their dense connections. And with the dense connection, it is indicating your feed. It is behaving like a feed forward neural network here. A fully connected layer, which is with the ReLU activation function. And then you have a fully connected neural layer with dropout. This dropout is interesting. I hope you understand. When we do a hyperparameter tuning, we are using regularization and dropouts. Dropouts, as the name indicates, the neurons, because if I feel they are not contributing anything meaningful, I can drop out that connection. And finally, I'm going to the classification, that the digit which I had seen as an input 2, what is the output which I'm getting? So this is the way that the deep learning neural networks, they work in convolution neural networks, and it is very, very easy to implement it in TensorFlow using Keras hypertuner. You can very easily develop a convolution neural network. So this is a network which will, these multiple convolutions, learning these convolution operations at every layer, and multiple such layers will make it as a convolution neural network. And we are learning the weights of the classifier also, as well as the weights of the kernel. That's precisely I said. Here, the question comes in that I here have a feed forward neural network, then I have certain hidden layer, and I will be doing a back propagation. Is the back propagation restricted only to the dense neural network? No. Is the back propagation learning is happening at a kernel level? Yes. Is this back propagation weight learning is happening at all channels at all kernel levels? Yes. The moment I say yes to this, it means I'm not dealing with handcrafted feature engineering. I'm dealing with weights which are updating my feature vectors also. So in the case of convolution neural networks, the learning is happening at a classifier level as well as at the feature extraction. So when programming a convolution neural network, the input is, we call it usually in the case of your TensorFlow, we will call it as a tensor with the shape, that is the number of images multiplied by image width and the image height and the image depth. After passing through a convolution layer, the image becomes abstracted to a feature map. I have told you what a feature map is. When you put a filter, when you put a kernel, and there are number of channels of the kernel and number of kernels, it is converting into a feature map with a shape, that is the number of images, the feature map width, feature map height, and the feature map channels. A convolution layer with a neural network will have attributes. Convolution kernels are defined by width and height. These are called as hyperparameters. The time is less, otherwise it needs a separate subject altogether. What are hyperparameters? How do we do hyperparameter tuning? What are the methods which we bear in mind when we deal with hyperparameters? The number of input channels and input output channels, again hyperparameters. The very fact that I'm dealing with weights, what should be my weight? How much weight I should be deploying? I can put a weight initially as 0.25. I may put a weight as 12. What should be the weight? These are all the subject matter of hyperparameter tuning. The depth of the convolution filter, the input channel, must be equal to number of channels, that is the depth of the input featured map. That is very, very important. And then I told you about the pooling. Convolution neural networks may include local pooling or a global pooling layer to streamline the underlying computation. And pooling, what it does, I showed you max pooling. So max pooling of 2 cross 2, it eventually reduces the dimensions of the data by combining the output of the neuron clusters at one layer into a single neuron in the second layer. Local pooling will combine small clusters of 2 cross 2. Global pooling will act on all the neurons of the convolution layer. So that's why local pooling means that it is working on a smaller clusters. As I showed you, a max pooling, you can always do a min pooling also. Min pooling means if you have a 2 cross 2 matrix and the numbers are 1, 2, 3, 4, what will be the output of that min pooling? It will have 1. And if you're dealing with the average pooling, then it will take average of 1 plus 2 plus 3 plus 4 divided by 4. That will be average pooling. And a global pooling, it does not work with the smaller clusters. In fact, it will act on all the neurons of the convolution layer. And pooling may compute a max or an average. Usually we work with a max pooling, or it can also go on a min pooling also, or on an average pooling. It is a form of a non-linear downsampling. Max pooling is the most common form. As I said, usually when we deploy pooling, it is usually the max pooling. Intuitively, the exact location of a feature is less important than its rough location relative to other features. This is the idea behind the use of pooling in a convolution neural network. The pooling layer serves to progressively reduce the spatial size of the representation, because your spatial size is also very important. Reduce the number of parameters, memory footprint, and the amount of computation in the network. And definitely it controls overfitting. As you know, when you deal with multiple layers and you deal with multi-layer feed-forward networks, you usually come across the problem of overfitting. And convolution neural networks, it tries to emphasize and have a control over the overfitting. The pooling layer helps us to control this overfitting problem, and the pooling layer operates independently on every depth slice of the input and resizes it specially. So that is important. So you can see I have just taken, for simplicity's sake, a single depth slice. So it's a single depth slice. If I am running a 2 cross 2 pooling on this and a max pooling, the first quadrant you can see is 1046. The outcome of the first quadrant is 6. It's a max pooling. Next is 2368. Output is 8. Next is 3112. Output is 3. Then you have 1024 and the output is 4. So max pooling uses the maximum value from each of the cluster of a neuron at the prior layer. In partition the input image into a set of non-overlapping rectangles. For each such subregion, outputs a maximum, and max pooling also performs as a noise suppressant. Now, this is an example of average pooling. Rather than max pooling, it is calculating an average pooling. And pooling is definitely, it has two effects. One is dimensionality reduction, and it also works as an agent for noise suppressing. Now, when I am talking about weights, you have gone through the complete convolution neural network. So in the case of convolution neural networks, the weights of the vectors and the bias are called filters. We don't call them now as weights, and they are usually called as filters, and they represent particular features of the input. And many neurons can share the same filters. As I said, when I say share the same filters, filters are what? Weights. And it means I am re-emphasizing these kernels are sharing weights. So convolution neural networks, one of the important thing is they have a weight sharing. It makes the job of learning much easier, and definitely because I am doing a weight sharing, it reduces the memory footprint. And the building blocks you have seen, convolution layer, it has a local connectivity, it has a special arrangements, parameter sharing, pooling layer, ReLU layer is very, very important, fully connected layer, that is your dense layer at the end, and then you have a loss layer where you will be computing the loss and you will be deploying the loss activation function. This is my ReLU function. Thanks to ReLU, because earlier we used to work with the sigmoidal functions, which was giving a problem. And that's the reason we were not able to deploy the hidden layers. And ReLU has made the life much simpler. So what is happening is if you have an input as an image, you're doing some convolution. It means you're connecting, having some feature maps kernels. From there, you are doing some subsampling. Subsampling will have by the help of the pooling. Then you will have again feature maps. Again, you are doing a subsampling. Then on to the pink color is your fully connected dense neural network. And then you get on to the output. The three hyperparameters, they control the size of the output volume. I'm calling it as volume because I'm dealing with height, width, and depth of the convolution layer. The depth of the output volume controls the number of neurons in a layer that connects to the same region of the input volume. And strides. Strides will control how depth columns around the spatial dimension, that is width and the height, are allocated. And zero padding provides control of the output volume spatial size. It helps to preserve the size of the input volume. The spatial size of the output volume can be computed as a function of the input volume size W. Suppose my input volume is W and the kernel width size of the convolution layer is K. The stride with which we are running is S. The amount of padding is P, and the formula for calculating how many neurons fit in a given volume would be W minus K plus 2P divided by S plus 1. It is same as W is because I'm talking about 3D. So that's why I'm calling it as volume. I'm calling it as W. So W in my earlier example, which I had told you, was N. Then I told you filter. Here I'm calling it as K. It is N minus F. Here I am representing it as W minus K. And then I was saying plus 1. So that is a formula. If you see very carefully, I'm talking of the same formula, except I've introduced two more things, which is now padding. In case if you have done the padding to restore the size to be the same as an input, so it will have plus 2p, and definitely it will be the strides with which they are applied, divide them by stride plus 1. So that will be the formula to say that how many neurons they fit in a given volume. With this, you will be able to compute. And the loss layer, everyone knows about the loss layer. It specifies how training is penalizing the deviation between predicted output and the true labels. And what you use is a softmax because you're dealing with multiple outputs. So we are deploying a softmax loss for predicting a single class from the mutually exclusive class. And sigmoidal cross entropy loss for predicting k independent probability values. So you will use a cross entropy or a softmax loss, or a Euclidean loss is used for regression. You know it very well. And choosing hyperparameters means the number of filters, the filter shape, and the max pooling shape. And can CNN be implemented as a feed-forward neural networks? I am posing a question and also I'm giving an answer. Yes, you can implement it as a feed-forward neural network. How? You look at it very carefully. On your right-hand side, I've given you a dense feed-forward neural network. What am I doing? I'm simply making a sparse connections by performing something which can be dropout. The light gray color, in case if I don't connect them, the light gray color connections, if I'm not connecting, so my feed-forward neural network is mapped as a convolution neural network. Intuitively, you may say so. Yes, so we can do it. Very quickly, I'm just introducing you the CNN architectures, that is LXNet, LENet, VGGNet, GoogleNet, ResNet, ZFNet. So basically, it started with the LENet, which was in 1998. So 7 convolution networks, and that was used in 1998. That classifies digits by the use of several banks to recognize handwritten numbers. So it used 7 convolution layers. See when it started at 1998. So this is the way it has been working. Then LXNet came into picture 2012. In 2012, and the network has an image input size of 227 by 227. And it uses 8 layers, as you can see. Then came in ZFNet in 2013, and it uses 7x7 size filters. LXNet used 11x11, but it gave a performance which was at par. Then VGGNet, 16 convolution layers it uses. So VGGNet is comprising of 138 million parameters, which can be challenging to handle. So, but even then, these, when every year, I am sure you must be aware that every year there is a competition which is held. That is your image, finding out which image is that. 1,000 plus images, millions of images are given, and you have to train your model to see how best you are able to give the output with the less error. So these all VGGNet, etc., they really work well. And using image classification using CNN, Google has come up with it, and it is a very powerful model called as GoogleNet, also using inception model and a ResNet. So this is the inception model which they have come up with. If I have this slide, which I can show you, and this is a GoogleNet which Google has given. And I just want to show that what is the output which we are getting and the error rate which we are getting. So with these kind of the, yes, error rates, when these models of convolution neural network came in, they were developed by whom? And then they were classifying the images. In LXNet, it has an error rate of 15.3%, and number of parameters which it trained was 60 million. I'm just going down to the GoogleNet, came in 2014. The error rate reduced to 6.67%. Number of parameters was 4 million. And if you look at ResNet, ResNet came in 2015. The error rate is 3.6%. In fact, it has beaten the human being also, because if a human being is also shown these many images, they are prone to have an error which is higher than 3.6%. As a very powerful convolution neural network which has come. And finally, my last slide, application of CNN. It has vast applications which are on image recognition, video analysis, natural language processing, anomaly detection, drug discovery, health risk, checker games, time series forecasting. Nowadays, when I was talking about speech synthesis, we are working on convolution as well as recurrent neural networks. A combination of them, it is working out very well. So thank you very much. And I hope it was informative. The time was short, so I might have rushed on to some of the slides. Thank you.
It was very informative. Ma'am, we have some queries from the audience. Can I read them to you?
Yes, please.
Ma'am, one of the query is that it is said that deep learning models are a black box. How can we visualize them in case of CNN?
As you see, apparently you see, if I am not developing, for me, it is just a black box. But I have taken you into the details of the convolution neural network. It is not really a black box. A lot of research is happening. Once you take a model, let's say you are working on inception net. On the inception net, now they have trained various hidden layers. You can do very actively a research you can try changing the number of hidden layers, the number of kernels, the strides, the pooling, the padding, and the dense layer. Again, the number of hidden layers, the kind of the activation function, the kind of the loss functions you can use, and you can do a gamut of activities on them. So it depends upon a person how you are taking these networks. So to my mind, they are, if I am a researcher, it is providing me plethora of opportunity to perform active research and change these parameters and see the result. Yeah. Next, please.
Okay. Thank you so much, ma'am. Ma'am, another query is, can convolutional neural networks be used for unsupervised learning? If you could please give an example.
Yes, you can use them for unsupervised. As I said, nowadays, a lot of things are happening. I don't feel contented and happy only with the convolution neural network. So we are building up model. For example, I am building up a model which is a speech recognition system. It has to recognize what a person has spoken and convert it into a text. So this is not an example of supervised learning, because I do not know what all he's speaking. I have to come up with an answer in the text form. So initially what we are using is a convolution neural networks and extracting the features, and then I'm deploying them to the recurrent neural networks and the RNN transducer, deploying autoencoders and decoders and getting an output. So the combination of models can help us to work on into an unsupervised arena as well. Next, please.
What are some advantages of using convolutional neural networks over other neural networks in an image classification task?
I think I have already spoken a lot
Yes.
about it. Number one, you are not working with the handcrafted features. You are actually learning the features. Number two, the sparse connectivity, which is reducing your computation time. Number three, the number of kernels which you are using, which will help you into the edge detection, image sharpening, and so on and so forth. And number four, the weight sharing. So these are very important advantages of convolution neural network.
Thank you. Another question has come. When should we switch from convolutional neural networks to RNN?
Two,
RNN, recurrent neural networks.
as I told you, it all depends upon the application. As I gave you a plethora of application, if your application is to deal with images, object detection, object recognition, a classification of multiple objects, if you want to detect a face or the movement of the face, even you want to flip the face, you want to zoom the face and then find it out, forensic applications, CNN is delivering and giving the best results. Wherever I'm dealing with the temporal data, the data which changes with time, there is a time sequence involved. In the case of your speech synthesis, speech recognition systems, and speech translation systems, machine translation system, speech processing systems, there what we will use will be recurrent neural networks. Yeah, next please.
Okay, thank you so much for answering all the questions, ma'am.
Thank you
If
very
the-
much. Indeed, it was my pleasure to be with the esteemed faculty members, because as Vice Chancellor, you are usually occupied with files, and taking decisions and working on a different set. But here, I always prefer to be with my own faculty members and talk something on research. Here, the last thing which I would like to mention is, if any one of the faculty members who have joined are willing to take up research in the area of speech, NLP, or in the area of face detection, they're most welcome. They can contact us and we can connect, because we are setting up a center of excellence in AI. And similarly, if anyone is having an interest in the drones on mechatronics, they can also contact us, because we will be setting up a center of excellence in mechatronics. And I believe the anchor or Professor Nidhi can share the email ID so that you can connect us on that email ID. Thank you very much for giving me this opportunity. I wish all the best and keep learning, keep discovering. Thank you.
Thank you so much, ma'am. It was really an insightful, thought-provoking, and interesting session for young researchers like myself. It is my privilege to propose a vote of thanks on this event. I, Palak, on behalf of the organizing team of ATAL FDP, extend a very hearty vote of thanks to the Honorable Dr. Mrs. Amita Dev, who blessed us with her presence and took out valuable time to present her topic on convolutional neural networks. Thank you so much, ma'am, for joining us and always supporting us. Thank you once again.
Thank you.